So now let us say resistor, that is one of the element we are using, device we are using in circuit design. So for a resistor, the voltage current relationship in the time domain is V is equal to IR. V is equal to IR. So that is why here is a time domain with respect to time. So V of t is equal to R times I of t. R is a constant value, so we are not making any changes. This is the representation of the voltage in time domain. The same, this is the representation of time resistor in time domain. Voltage across the resistor. So now if you take the Laplace transform, then what will happen? A Laplace of this L is representing the Laplace transform. L of V of t is equal to L of R times I of t. R is a constant, you are taking it outside. So R times L of I of t. So we know in the Laplace transform, we are representing everything in terms of complex numbers. Yes. So then this V of t, we can represent as a capital V of S. Remember, this is capital V of S is equal to R times capital I of S. So this is what you have to remember. So this is the equation 1 in time domain. This is the equation 2 in S domain. So you are representing the resistor like this in time domain, and in S domain you are representing this resistor like this. What is the physical units? Physical units V of S is volt seconds, and I of S is in ampere seconds. So this V of S unit is in terms of volt seconds, and I of S unit is ampere seconds. Resistors are behaving the same in time and S domains. So it's almost the same. V of t is equal to R times I of t. V of S is equal to R times I of S. It's behaving almost the same. It's more easier to represent the resistor from time domain into S domain. So it's very easy. Try to remember these two formulas. We are going to use this in all the problems. So try to remember this. And the equation 1 and equation 2. This is for resistor. Now inductor. So how can we represent the inductor in time domain? V of t is equal to L times d I of t divided by dt. So remember, V of t is voltage across the inductor. L is the inductance value of the inductor, and this I of t is current flowing through the inductor. Similarly, here in the resistor, V of t is the voltage across the resistor, R is the resistance value, I of t is current is flowing through the resistor. Similarly, here just we are representing this in S domain. So inductor, this is how we represent in the time domain. In S domain, so we need to take the Laplace transform of this equation. Laplace transform of L of V of t is equal to L of, and here L of L I dash of t is equal to L, we can take it outside. So L times I dash of t. So do you know what is this? How we got this? We are taking the Laplace transform of this. So Laplace transform of this entire term. So L is the constant. So L is just outside. So Laplace transform of this I of d. This is what? This is the derivative of the current, right? D by dt means this is the derivation. We are using the derivative form. So derivative, one time derivation. So we are making this I dash. So L of I dash of t. And this is the time domain. Still we are in the time domain. Now we have to represent, or we have to convert into the S domain. So V of t is converted into like this. Capital V of S is equal to L times, that is the constant inductance value. So if you make Laplace transform of this part, then what will happen? S times I of S minus I of 0. This is the Laplace transform of this signal. So now we can just separate this. So L, S is also constant. We are taking outside. S times L, I of S minus L we are bringing inside this bracket. So L times I0. So this I0 is called initial current of the inductor. So if you simplify this equation further down, then you will get like this. I of S is equal to 1 divided by SL V of S plus I of 0 minus divided by S. So this is the Laplace transform of this inductor. So whenever we talk about the inductor, we are talking in terms of the current. So I of S is equal to 1 divided by S of L. I of S means what? That is the current flowing through the inductor is equal to 1 divided by S times L. S is this. This is the time S domain representation variable, and L is the inductance value. V of S is the voltage across the inductor, and I of 0 minus means that is the initial current across the inductor. So you know inductor, how the inductor works. So inductor like this. So maybe you are applying some kind of voltage plus minus. Let us assume initial current. Before I start to apply the initial current, initial situation or the initial condition of this inductor is 0. So I0 means at 0 time constant, the value, the current across this inductor is 0. But now I have the switch here. Let us assume I have a switch. So now the switch is not on, switch is open. So now I close this switch. So now it's a short circuited. So now this current will start to flow through this inductor, right? So then this is called I of t. And whatever the voltage, so when this current is flowing through the inductor, what will happen? The inductor will start to store the energy in terms of magnetic field. So in any conductor, if you apply the current, it will start to store the energy in terms of magnetic field. So this magnetic field is because of this electrical current. So we can call this as a electromagnetic field. Electromagnetic field. So I am sending this, the switch is closed now. So this current is charging this inductor. Similarly, if you have the capacitor, same. So you will charge the capacitor instead of the inductor. Inductor is storing the energy in terms of electromagnetic field. Capacitor is storing the electrical energy in terms of charges, electrical charges. So after some time, I open the switch. Now the switch is open. Now this is open circuit. Then what will happen? This already the pre-stored energy, the magnetic field will collapse. Then this inductor will collapse the electrical this field, and then this will flow in terms of current. So this is what happening in the inductor. The same operation, similar operation is happening in the capacitor also. Okay, so now whenever we have the inductor like this, the inductor has certain value, right? L, maybe L is equal to maybe 10 millihenry. This is the unit of, we measure the inductance in terms of henries. Henry is the guy who invented this, so we call this a Henry. So millihenries or microhenries or whatever. And the capacitor, of course, the unit is farad. So it's a millifarad or nanofarad or microfarad. So the capacitor unit is different. So now you should know this. Though L times I of 0, this means this is the inductance value. If I have the 10 millihenries, so 10 times, the initial current before I close the switch, whatever the current across this inductor, that is called initial current. So in this assumption, I assumed this is 0. So I naught is equal to 0. So 0 times L, that is 0. But here you have this S, L, that is the inductance value, and the I of S, that is the current across flowing through this inductor. So anyway, you have to remember this formula. I of S is equal to 1 divided by SL times V of S. So this is the formula for inductor. And of course you have plus I of 0 minus, that is the initial current. But in many situations, we assume the initial current across the inductor as 0, but not always. Sometimes we also have to consider this term. But you should remember, whenever you have the inductor in this time domain, when you represent in the S domain, you have to use this formula, 1 divided by SL V of S. Note here that the initial conditions can be represented either as a voltage or as a current source, the initial condition. Now, this is the equivalent circuit for an inductor, equivalent circuit. So here you can see this is the inductor L, and we have in the time domain. So this is called time domain, and this is called frequency domain or S domain, sequential frequency domain. So I am applying the voltage V of t. Because of this voltage, there's a current flow I of t across this inductor L. The inductor inductance value is L. Maybe it's some kind of some value, maybe 10 millihenries. Let us take our example. I of 0. What is I of 0? This is the initial current before we apply this voltage. So that is the I of 0. So you should know now what is I of t. Initial, this I of 0 is the initial current. I of t is the current flowing through the inductor L because of this applied voltage. So now I have to draw the same circuit inductor in frequency domain. So the same, everything is the same. And SL, remember here we have the SL the term. So I have to multiply the inductor value with the SL, and then here I have this plus, remember here plus minus, the polarity is the opposite, and this is the initial current in the inductor, L times I of 0 minus. So this is the time domain representation of the inductor, and this is the frequency domain in, representation of the inductor. So SL, L times I minus I of 0 minus, and the voltage V of t is capital V of S, and current I of t is equal to capital I of S. And this one we can also rewrite the same equation like this. So we are putting this current source as a parallel. So here we have the V of S, I of S, SL, that is the load inductor, and this initial current we are putting in parallel. So that is I of 0 minus divided by S. So time domain, that is the A, and then the S domain, this is the series. This is the series. Now we are considering the initial current in terms of series, and here we are considering the series current in terms of parallel. So this is how we have to represent the inductor in S domain. S domain is nothing but the Laplace transform of the time domain.